So what's that? Let's go bold here. What'd you get?
1.0507.
1.0507 units.
Radians?
What do we find?
Period.
The units?
Second.
Yes.
How did you, where did the equation that you circled, where did that come from?
I know that F equals ma. We had Ft cosine theta is equal to mass times the centripetal acceleration. There are two formulas for centripetal acceleration, and that's one of them.
Oh, okay.
So when we did the substitution, then the radius was L cosine theta, because if we look physically at that triangle, this was L, this is theta. R was this distance right here. So that's the hypotenuse times the cosine of the angle. And then cosine canceled out.
Okay.
And so that will have to tension, and then m omega squared L.
So it would have been an R if it weren't at an angle. Yeah.
Right, and if not at an angle, this cosine theta wouldn't have been here.
Okay.
Yeah, if on the first problem we did where there was no gravitational pull, those wouldn't have been there, and that would have been R.
Okay. Thanks.
Questions? All right. We're going to do a lab on Thursday, the centripetal motion lab. This is not exactly what we're doing, because we will know the tension, and we'll actually be plotting omega squared versus the tension. We'll know the length, and then we'll try to figure out what the mass is and compare that to the actual measured mass. So it's the same type problem, just we're looking for something, something different will be given.
So on Thursday, we're still doing chapter 6, correct? In here, anyways, like in person.
We'll be doing a lab.
And it's on chapter 6, like.
Yes,
Thursday.
it's on chapter 6.
And then on Thursday, we also have the Master Set 7 due. Would you be willing to consider pushing that back? Just because, which I know we have the chapter 7 videos online to watch, but.
And they are absolutely thrilling and spellbinding. Yeah, do the following Tuesday.
Okay.
Okay. Any objection?
No.
Oh, I've been wanting to ask this. Of the people in here, how many of you prefer the 8-week class over the 16-week class? I guess your choices are, I like the 8-week class, I like the 16-week class, it really doesn't matter.
It's a lot.
So, 8-week,
Normally, I like the 8-week, but not for physics.
Yeah.
Six-
Yeah.
yeah, I'm talking for physics, 16-week. Okay, because I was realizing, I have my own personal bias, I don't care for the 8-week class, but the students who are struggling, 8-week class doesn't work for them, and I think, well, I actually don't hear from everybody, and I didn't know if the other people really like the 8-week class for this, but, okay.
It's just a lot at once.
Yeah.
Yeah, okay.
You should try to redo this class, but this semester. You should sign up for these classes for semesters and participation.
Yeah, I'm hoping they'll eventually give departments the decision of, do you want it to be 8-week class? As opposed to, it's going to be.
That would've been nice if we had an option too.
Yeah.
Yeah. Thank you for moving chapter, Masters at 7.
Oh.
But also, on the
Yeah,
20th,
Masters at 8.
but Masters at 8 is supposed to be due, where you moved chapters.
And you have a problem with 7 and 8 too? What?
'Cause 8 is a little long.
8 is long. Oh.
8, that's momentum? Or
Yeah,
energy?
momentum. Yeah, it's this one.
I guess 7 is energy, 8 is momentum.
How
Yes,
long- how
7
long
is
is-
work and energy.
How long is 8? Okay.
Yeah, but that last page, that's just one problem, right?
Okay.
There's 2 on here, but like, I
Okay.
guess that's because I printed, but.
Yeah. You know, if I took the diagrams out and took out the picture of Bill Chambers, then,
Number 6 is kind of low steps. So.
Okay. It's doable. We've come this far.
I'll just, let me, I don't have my calendar in front of me, well, so at least 6 is due Thursday, and then the rest of it, Thursday ask again.
Okay. 6 is due Thursday? Oh, okay.
I was writing down.
There's the dream schedule in my head before I start the course, and then there's reality once, you know, I'm actually dealing with people. But they insist on my having a set schedule before the course begins.
So you wanna do 6 and 7 on Thursday, or just 6 and then 7 on, 7 and 8 on
We'll cross
Tuesday?
that before we get to it.
Yeah, 6 is due on Thursday.
Yeah.
7 is due next Tuesday.
With 8?
So far, yes.
Yeah,
Okay.
Thursday I'll potentially make an adjustment.
And
Or
then-
I'll look at it and go, this group is the best group I've ever had, they can handle it.
There'll be a test that Thursday, right?
Yeah, I need to look at the whole schedule to figure out that stuff, so. Come on. So what's another test, now that you're recovered from the first one? All right, so the thing swinging around is a classic centripetal motion problem. Another classic centripetal motion problem is the car on the ramped track or banked track. And, but I also want to get into the gravitation aspect of it, because I believe gravitation is also part of chapter 6. Okay. Some textbooks put gravitation off to the rotation part. So I at least want to talk about that. So let's talk about the generalized formula for the force due to gravity as opposed to the one we're using right now of mg. We can now expand on that.
So the one, okay, you're gonna hear it. I was just gonna say the one with mg is due to acceleration.
That's acceleration due to gravity.
Acceleration due to gravity, okay.
Yeah, this formula would always work, but if we're talking about what's the gravitational force on our moon, figuring out what g is not particularly easy. You actually would need that in order to figure out this. We're talking about the acceleration of the moon because of the Earth, not the acceleration due to gravity on the moon. So when you are dealing with celestial bodies that are far apart, we can no longer use 9.8 if it's dealing with Earth, or 1.6 dealing with the moon. The accelerations are much smaller, potentially. So Newton figured out that gravitational pull really depends on how close they are. The closer objects are, the greater the gravitational pull. So as the distance gets smaller, my force gets bigger, so R would have to be on the bottom. Matter of fact, it's R squared. There are some physicists trying to figure out, is it really squared? Maybe it's 2.01 or 2.001. 2 is just a rough estimate. So there are people who do try to figure out if it really is 2 or not, and all they come up with is that the difference between the actual number and 2 is less than, and then it's like 0.000001. It's close enough. Except for those people. He also figured out that the force depends upon the mass of an object. But since forces come in pairs, if I've got Earth-Moon situation here, the Earth is being pulled towards the Moon's being pulled towards the Earth's being pulled towards the Moon. Both masses have to be involved. Since commutative property should hold, since I should be able to switch the objects and the force is the same, Newton's third law, I have only 2 mathematical properties here, or operations, which commute. 2 things where I can flip the order and it doesn't matter. And mathematically, what are the 2 things? What are the 2 operations?
Multiplication,
And,
division, oh wait, no, addition.
yes. And it turns out it's multiplication. Now, if you notice, I've got a big gap right there in front, and that's because I'm going to end up in newtons. I have kilograms here times kilograms. I have meters times meters. But there's got to be something else involved. And so this is the third thing, which students often call gravity. Matter of fact, on the board here, we have big G, little g, W, F sub G. And I do want you to be able to distinguish between those 4 things and not just call all of them gravity. This big G here, the name has changed slightly. It's called the gravitational constant.
M1, M2 is just mass 1 and mass 2.
Yep. And I'm going to parenthetically put universal in front of it. I don't think that is used anymore. Textbooks I did when I first took physics called it the universal gravitational constant.
This one still says it too.
It still does? Okay. There has been called into question whether it is indeed universal or whether this is just, the value for it is just local in space. Is it the same thing in another galaxy? We know that things are behaving differently than we would predict based on what we can see. So there's got to be some reason for that. The current theory, the paradigm in vogue at the moment is the idea of dark energy and dark matter. And there's definitely experimental evidence for those existing. But it's rather arrogant of us to think that we've got the universal value. It's like UTC, Universal Time Code. Yeah. Like we were establishing time for the entire universe. Sorry about that. All right, the value of G in SI units is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. It's nice to know that on a quiz or test, or on a master set, you would just look it up in the book or type in universal gravitational constant. But on a test, it would be at the top of the first page, or near the top. All right, so if this formula is correct, there's a gravitational pull between any 2 objects in this room. So why don't we take my mass, well, myself, mass 1, I'm about 100 kilograms. Actually, no, I'm closer to 90 now. I've lost all my pandemic weight. Was approaching my wedding weight, but then I started eating snacks again. And the mass with me, and well, we've got a half kilogram mass right there. So what is the gravitational pull between me and the mass that's sitting about 3 meters away? Well, it's a plug and chug. So the force due to gravity between me and that little mass over there right beside the camera, 6.67 times 10 to the negative 11 times 100 times 0.5 divided by 3 squared. If someone would be kind enough,
I got 3.335 times 10 to the negative 10th.
anyone else
I'm getting an E,
getting E as an error or E negative 10?
E negative 10.
Okay, that,
So
same
I
thing.
did get 3 point, yeah, I got that one.
All right, units?
Newtons?
Yeah, it's a force. Also, the units of this, the meter squared cancel out from the radius, and kilograms cancel out from the masses. We'll have to newtons. All right, so that is the gravitational pull, and so we're talking 1/3 of a nanonewton force between me and that mass right there. And I'm, no, I don't want to brag, but I am strong enough to overcome that. Apparently all of you are as well. Now let's talk about the force between me and the Earth. Now I'm not going to use the simple little formula here. Let's go ahead and use the big one. The force between me and the Earth. So I have 6.67 times 10 to the negative 11th times my mass times the mass of the Earth, 5.98 times 10 to the 24th, divided by R. What is R with me and the Earth?
0. Are you talking about the center of the Earth?
That's ultimately the way I'm headed.
6,000 something. I can't remember the whole number then.
All right, so we basically between, what number are you trying to come up with?
It's like 60, it's around 6,500 kilometers.
Where's that coming from?
The textbook. Probably the textbook, they were saying the Earth's radius.
Radius of the Earth, that's what it's
Oh,
happening.
okay.
So we have radius of the Earth versus distance to the ground. If it's distance to the ground, if I walk outside and I put my hand on the ground, then R would be 0 in that case. What would happen to the force?
0. Once you put 0 at the bottom.
NA, because you can't divide by 3.
All right, suppose I'm 1 centimeter away from the Earth, from the surface of the Earth. If this denominator is incredibly small, what happens to the force?
Big, because you have to divide a big number into a small number.
Yeah. So it can't be the distance from me to the surface. It's center to center. Technically, center of mass to center of mass. So it would be the radius of the Earth, roughly 6.4 times 10 to the 6th meters, or 6,400 kilometers squared. I think 6.37 or 6.38 is a little bit closer, but 6.4 is good enough. At least for this one, I know roughly what the answer is going to be. Oh, I suddenly did I said 90 kilograms for myself, and then I stuck in 100 both times. I guess let's change that back to 100. Middle of pandemic week.
973.79?
973 point something,
79, yeah.
79 units.
This is the force.
newtons.
Yep. All right, if I'd done it the other way, if I just found my weight of mg, well, my mass is, well, I guess I'm sticking with 100 now. G is 9.8. There's a rounding difference there. This is, I think this is the place where it's a little bit off, but that's been rounded off, that's been rounded off, this was rounded off a little bit more. But I hope you could see that those are roughly the same value. And so if you're near the surface of the planet, then yeah, I can just, mg sounds fine. But if I'm not, I need another formula, thus this one. Questions before we actually combine this with what we had done earlier today? The time is right, correct? Yeah. Earth. Satellite. The distance here, some distance on. If the satellite is in orbit around the Earth, what is the speed? How fast does it need to go? Speed of the satellite. There is an ideal speed for a particular radius. I am assuming nice, perfect spherical symmetry here. If this satellite's going faster than the formula we come up with, then it would move farther away from the Earth. If it's moving slower, it would slowly, the orbit would decay and crash into the Earth. So let's do the force diagram. What are the forces acting on the satellite?
Earth? Is it the force of the Earth?
Earth is object. What?
Gravity.
Yes,
Gravity.
from the Earth. Not putting W down because weight doesn't really make sense here. Anything else?